Okay. This is an interesting piece here when we think about it. We're going to get this normal distribution, right? They're lumping up in the middle. But each particular little ball bearing bouncing down there, that exact path, the path it took, that has a chance of 1 over 2 to the t, right? The exact path, right? So the specific whole history of that walk is very special, but it just turns out that there are many that will end up in the same place. So when we say, oh, we're only interested in where it ends up, then we get this normal distribution. If you want to say, what's the chance of this exact walk? Well, it's not interesting. Each walk is, right, has exactly the same chance of happening, including the walk which is all heads out this way or all tails out this way, which we would think was super special, but is not in terms of the entire history of the walk. It's just, one of them. Yeah. Right. So that's an important thing. So, but we're interested in how many walks end up in the same space, and so we're going to have to write a few things down. So this is going to be the we can set this up. The number of walks that start at I and end up at j after t time steps. So it's going to allow us to be kind of anywhere in this thing. So imagine we're here. This is I on our x-axis, and j is here, and we say, all right, time is 10. How many walks can get between here and between I and j in that time? And if it's an even displacement, and we have an odd number of steps, then it's not going to work. So we have to accommodate that. So what we want is, right, we want the walk to have, it doesn't matter how it gets there, we just need that it has to have, at the end of t time steps, has a displacement of j minus I. Okay, so you can figure this out. It turns out to be a binomial, right? So there's t up here, choose t plus j minus I divided by 2, given that it's possible. All right, so it's a fun thing to work out. Just a little bit of counting stuff. I know, and if you haven't done it, it's all right. We'll get through it. Binomials are good things. So that's a general, so we can write down this general thing, and then we can start working with how this behaves. Okay, so we're going to say just let's take even numbers. What's the distribution like? So all we can have is 0 and plus or minus 2 and so on, and this is plus or minus 2n. That's the case where we've only had all heads or all tails. Okay. Right. So yes. So it's going to be even. So we'll just sort of frame it so it's clearly even. And we can start. Let's start at 0. Fair enough. And we have t time steps, and we're going to get to this 2k here. So what's the probability that we get to 2k? And using the expression that we had before, right? We have nijt. Put all those things in. This is our time. We have 2n time steps. And if you go back, we'll put all that in. And so this is another assignment question. So for large n, you have to think about how this behaves, right? So there's going to be, n is large, so this piece is growing and this piece is growing, and you want k to be kind of in the middle, right? Comparable to n. There is these extremes, right, where there's just sort of one sequence of heads or one sequence of tails, but we're interested in that middle bit, so we get the normal distribution of Snortum. So all of this will pop out, and we'll get a root pi sitting in there and all those things, which always seems very magical, but is a spectacular achievement of humanity. So, and that's the normal distribution, right? So that pops out of these little ball bearing things bouncing around. So that's pretty great. It's a nice thing. And I think I have it on, it's nutritious. There you go. It turns out there's a whole bunch of other things that are related to this that are called stable distributions. Let me just briefly say what they are. So if you have two Gaussian variables, two variables distributed normally, and you add them together, then you get another normal distribution, right? And the technical thing we do there is convolve the distributions together. So that's a really deep thing, right? We add the means add and the variances add. That's what you end up with. But you get a Gaussian back. If you add two exponentials together, that you start to mush them together, you get a messy looking thing. And if you add enough exponentials together, you get a Gaussian, right? So all of these, that's the central limit theorem. So we've just used we started with a plus or minus 1 thing. It's discrete, and we're smoothing it out. It's plus or minus 1 thing for, or heads and tails. That leads to a Gaussian. But the central limit theorem is more general. And any distribution, any set of distributions where we have, they're well behaved, they don't have a large variance, you add up all these samples, then you'll start to get Gaussian. Now, there are all these power law ones with power law tails that don't do that, right? They have infinite variance. And that's this little field of stable distributions, Laplace distribution, the inverse Gaussian. There are a few others. And they arise in real phenomena. So that's a nice thing to know about if you want to get excited about stable distributions. All right, this is a picture of what we've gotten to just now. So here's example random walk. And then we think about all the random walks that got to this point in time, and this point in time, and this point in time, and then bin them, make a histogram for them. And so it's going to tend to become a Gaussian distribution. Obviously, there's limits to the tails of this thing. It's not perfect, but it's going to become more and more fit by a continuous Gaussian. And the width of this thing is going to be growing like the square root of t, and that's indicated by this line here. And square root of t is the standard deviation. So for Gaussians, plus or minus 2 sigma is 95% of the range. I think, what is it, 60-something% for plus or minus sigma, and then 99% for plus or minus 3 sigma, just to give a sense of what they are. So this is well understood now, right? I mean, you have to do some calculations in here, but we have a good picture of this thing. So, and then really fundamental thing, we're talking about diffusion. This is a very fundamental kind of spreading, right? So most things left to their own devices will kind of smudge out. This is second law of thermodynamics, right? Entropy increases. This is part of all of that. We're going to get later on to contagion and spreading, and so that's a much more elaborate version of this. This is just a relaxation. But even simple diffusion on networks is an interesting thing, right? Where you just sort of throw some stuff down. You imagine Lemmings, the game Lemmings. This is pretty old school. Lemmings, where you just let them all run wherever they want to run. So that's the idea. You just pop them down on a node and let them all run, and then you have to think about where they all end up. And that's actually how Google worked originally. Google's got all these contraptions on top of it. Basically, it was all these little random walkers running around on the web, on their version of the web. So, which becomes a linear algebra problem, but it was really this thing, on a network, and it got a long way. Okay, so. Random roads. So we've got these sorts of things. We understand where these come from, but a lot of, I know I have these before. So random walks are a little stranger than you might think. So let's just finish with this setup. So this is the probability that at time step t, a random walk has crossed the origin r times. So you have to think about what that might look like as r changes, right? So that there might be a sweet spot, for example. So it's being t time steps, it clearly can't be like it's got to be less than t, or even less than t over 2, right? You've only had this long. So how many times could it wiggle across? We know it sort of wiggles around a little bit. And so the strange thing about this, so think of this, we had the 10,000 coin flips before. So, and this connects to this gambling thing. So if you're behind early on, what are the chances you get back to right? We make a comeback. So the most likely number of lead changes is actually by themselves. It's 0. It's monotonically decreasing. So the most probable number of lead changes is 0. It's a bad situation. It just doesn't feel like this is what it would produce. If you sum up all the probabilities of 1 lead change, 2 lead change, 3, right, then that's greater than this. But but this is really the weird thing, and I said it the other day, but the expected time between tied scores is infinity, which seems very strange for a random walk, because we're tied. You could go this way or this way, right? Head, let's say tail or head, and then you flip again. Half the time you come back to a tie, right? So half the time between two ties is 2. And then, a couple more time steps, you'll still get some coming back, and then so on. But there are some that will take so long and so long and so long and so long that when you take the mean of it, there's such a heavy tail in this distribution that the mean will be infinite, which is really odd. And so the exponent we'll see that we'll get to for this is that it decays like -3 halves. Right? So the probability that you have a tie that you first have a tie, that you first come back to a tie after 2n, let's say t time steps, will decay as t to the minus 3 halves. So minus 3 halves, right, that's between 1 and 2. Right? 1 is the edge of what we can get to. We can't even normalize that. 2 is the threshold where the mean becomes infinite. The variance is certainly infinite. So with probability 1, it comes back. It's just, on average, you'll have to wait, for an infinite amount of time. So it's a very strange little distribution, but it's a nice thing to work through. Lots of good things. So fellow is what I recommend if you want to go and get really excited about. Random walks. You don't have to do that. All right.